our statistics class. Yesterday we stopped at properties of normal distribution, and of course we're going to continue from there today. So I think we started normal distribution. It's a probability distribution for continuous random variable, and of course it's a distribution that is very popular uh, within, I think, in the research world in general, because most of the real life phenomena can be modeled by normal distribution. So I remember yesterday actually, um, walk you through the probability density function for normal distribution. And of course, not only that, um, I also so if you take a look at this guy now, that is the probability density functions of normal distribution. Okay, give me 1 second, let me see. Okay, so now the next on the line is actually, I remember, is property. Okay, normal distribution, in normal distribution, all the measures of central tendency are the same. The mean, the median, and the mode, of course, they are approximately the same. And if we want to look at the peak of the distribution, that very peak represents the mode. That's why I said the mode is the point on the horizontal axis where the curve is a maximum. And that will occur at x equal to mu. It is symmetric about vertical axis through the mean. And of course, it has the point of inflection. Give me 1 second. So it has the point of inflection at this. Okay, which means the point of inflection is actually S equal mu plus or minus sigma. Okay, this is where the point of inflection will take place. It is concave downward if you know if S is within one standard deviation. So if you take a look at this, that is within one standard deviation, otherwise it's going to be concave upward. So it can be concave downward or concave upward. And of course, the total area under a curve has to be equal to 1. So which means when I perform antiderivative on normal density, it should give me 1. That's what it means. Okay. So if you take a look at, for instance, if they ask you to evaluate this, okay, if they ask you to evaluate what you're seeing right now, okay, the idea of a normal distribution can actually be used, because in normal distribution, there is exponents like this, okay, but I'm still going to walk you through, all of that, okay. Now, but if we have a normal distribution, um, give me 1 second. If I have a normal distribution with these two parameters, because normal distribution has two parameters, the mean and the standard deviation. Okay, so if I want to use normal distribution to do anything in statistics, I have to understand the mean and the standard deviation. They are the two parameters. So, and that was why I call, they represent the mean. Okay, the mu represent the mean, the sigma squared represent the variance, and of course the sigma is the standard deviation. Okay, just wanted to take note of that. The mean is the center. Why movement away from the center can be measured by the number of standard deviation. Okay, can be measured by the number of standard deviation. Okay, so I'm gonna move right now. Now, let me tell you this. Because standard normal distribution, it may be difficult to use normal distribution to compute probability because you know, it's actually going to be calculus intensive. Okay. Now, I'm going to do this. I'm going to make use, it's like my iPad is not cooperating today, but that's okay. I'm going to use the board. Okay. So, let me tell you this. If I actually have X follow normal, okay, it means X follow normal distribution with mu and standard deviation. So f of s is 1 over square root of 2 pi sigma squared, okay, this. Okay, this is the density function. Now, if for instance, I want to find this, okay, I'm actually going to perform an antiderivative on this. If I perform an antiderivative on this, I'm going to get, so what I want to find here is the probability of X lying between, S lying between mu minus sigma and mu plus sigma. Okay, this is going to be calculus intensive. Okay, but let me tell you this, we have a way out. But I'm going to tell you the information this guy is giving. There's another one. Or if I want to find X lying between mu minus 2 sigma and, mu plus 2 sigma, okay, then I'm actually going to have this mu plus 2 sigma 1 over square root of 2 pi sigma squared this S minus mu sigma squared ds, this should be 0.95. Okay, and if I have mu minus 3 sigma less than s less than mu plus 3 sigma, okay, where mu minus 3 sigma mu plus 3 sigma 1 over 2 pi sigma squared, this guy, s minus mu all squared, the s is going to be 0.9975. Now, let me tell you from what I'm displaying now, if data set follow normal distribution, we expect that 68% of the observation should fall within one standard deviation. We expect 95% to fall within two standard deviation, and we expect 99.75% of the data to fall within three standard deviation. When that happens, then we say the data set followed normal distribution. So this is by empirical rule. Okay, that is by empirical rule. So by empirical rule, if I want to figure out if set of data follow normal distribution, okay, I want to be able to see if 68% of the data set are within one standard deviation. How do they find out that it's going to be 68%? They perform an antiderivative on this, and they use that as a lower bound and that as the upper bound, and the result we have is 0.68. But let me tell you this, without going through all this, because if I'm to walk it through how they got is 0.68, it's going to take forever. So because of that, we need to standardize. The approach of standardization is going to work. Now, I'm actually Um, going to go back. Give me 1 second. Want to go back to the material. 1 second. Okay, so I'm gonna share the material. Okay, so now because of the mathematical complexity that has to do find using normal density to compute probability, we can standardize. Okay, now why do we need to standardize our data? We need to standardize our data for mathematical or simplicity, because working with a normal distribution density, we're actually going to get into rigorous calculus technique, and that's going to take forever. Now, I present to you standard normal distribution. Okay, now take a look at this. If X follow normal and I want to standardize that, what I need to do is to subtract the mean from S and divide by standard deviation. So with that, I'm going to have a Z score. Okay. Now, the distribution of a Z score. Now, if X follow normal distribution with this, and what I'm going to have is that after standardizing, Z will follow normal distribution with a mean of 0 and a standard deviation of 1. Okay, now this is the standard normal distribution. What has happened here? In the conventional normal distribution, we plug in mean to be 0 and standard deviation to be 1. Then you're going to have this guy. Okay, now you can see that it's a little bit not complicated. Okay, now if I have that, standardization actually facilitates easy probabilistic computation. I'm going to say that again. Standardization facilitates easy probabilistic computation. Okay, that is why we're standardizing. Okay, now if after standardizing, let me tell you, if I want to achieve this guy here, if I want to achieve this guy after standardizing, okay, now instead of me, okay, to use the calculus here, let me stop my share so that those are on that are online. Okay, so instead of me to actually use, for instance, the calculus here, what I'm actually going to use will be different. If I want to figure out this, don't forget, Z is what? X minus mu over sigma, right? Now, and mu will be 0, sigma equal to 1 under standardization. The distribution is now going to become this. Okay? The distribution is going to become this. Now, this guy will be replaced by the probability of Z lying between -1 and 1, instead of the probability of S lying between this and this. Okay? It's going to be between Y -1 and 1. I need you to come back here. Wherever you see mu, plug in 0. Wherever you see sigma, plug in 1. What happened? If I plug in 0, 1, that would be -1 and 1. So I'm going to have this guy. And the moment I have this guy, it is the same thing as this. That I can just check table, normal table. I'm just going to check normal table. I can just check from statistical table under a z-score 1. Then I check under, is this called -1? When I subtract them, that will give me 0.68. Now that will save us rigorous process of conducting calculus. Can you see that? And for the two standard deviation, it's going to be between -2 and 2. For three standard deviation, within three standard deviation, -3 and 3. So if I were you, why can't you try that? Okay. Now I want to move right now back to the material. Okay. Now, if I now want to find probability associated, so which means if I want to talk about norma, if I want to compute probability associated with norma, I'm going to be doing probability associated with z-score because I've already standardized. Standardization will make your probabilistic computation easy. Now I want to show you something. What do we normally want to find when we're working with the z-score? Do we want to find the probability of z less or equal to? Don't forget, less or equal to is the same thing as less than. Does that make sense? It's the same thing as less than, the less or equal to. Okay? It's the same thing as less than. So don't forget that. Now, it means I'm on the curve, I'm going to the left. That's why you see the green shaded. Okay? That's why you see the green shaded. Now, I need you to pay attention. If you take a look at this, if you look at the green, that is between A and B, right? That's why you have this guy. Between A and B, right? But you know what? If you go from A to the left, it is this guy. Okay, B to the left. You see that? We can also do B to the right. B to the right, that will be greater than. Okay? And let me tell you this. If I want to find probability of Z greater than, I can use the law of complement. It's going to be 1 minus the probability of Z less or equal to. I can check for that in the table, in normal table. Of course, in the exam, I'm actually going to allow you to use a normal table. Has anybody seen a normal table before? Okay, it's going to be easy. Okay, the moment we have, we have that standardized. Okay. Now, if you take a look at this one, when you take a look at the green shaded one, and this is A, if I want to go to the right, then I'm talking about greater than. If I want to go to the left of the IO, on the unshaded part, I'm talking about less or equal to. And don't forget, the total area under a curve is what? 1. So the probability of this guy plus probability of this guy will be equal to 1. So if it is equal to 1, if I want to find any of that, it's going to be 1 minus the other. Does that make sense? Now I want to move right now. Now, I think I've said that. That's being repeated. Now, I want to also say this. The probability of Z greater or equal to A is the same as the probability of Z less than -A. They are the same. Greater or equal to positive is the same as less than negative in probability, here. So pay attention. Okay. Less than negative, you see the area. Greater or equal to A, you see the area. They have equal area. Can you see the green one? They have equal area. Even though that occur in opposite direction, but the area covered here is the same as the area covered here, and that's why we said they're going to be the same. Any question on that? Any question? Now, another thing I wanted to see, I told you the other time, if any continuous random variable, the probability that it's going to take an exact value is always going to be 0. And I also told you, this guy, whether they are open at both ends, they are all the same as that. Please pay attention when it's continuous. They are all the same as that. They are all the same. Okay. I wanted to take note of that. They're all the same. Okay. Now I'm actually going to move right now. Now, I think I've explained this to you extensively. Okay, they're all going to be the same. Now, this is an example. Now look at what they told you here. They suppose that Z follows standard normal distribution. For standard normal, the mean is 0. The variance is 1. Now, they wanted to figure out what is the probability of Z less or equal to 1.05. We're going to check table. Okay. Now, let me tell you this. If I want to check this one in the table, less or equal to 1.05, let me do this. You can go to Google. You can go to Google and just click Z standard. Okay, can you see that table? Okay, and let me see the one. You can open. I think I love using the Arizona one. The Arizona one has both negative and positive. Okay, let me download that. I'm gonna download that. Okay, now what do we? This table supports less than. If I want to check for greater than, whatever I check, I will subtract from 1 from this table. What did they tell us that time? 1.05, right? Okay. 1 point, you're going to check 1.0 under 5. Okay, this is 5. Okay, then I'm going to go all the way to the one of positive. Do you see here? Do you see 1.0 under 5? Then my answer is going to be this guy. That is the probability. So that is the probability of a Z, okay, less than 1.05. I'm just going to check the table. Imagine if I did not standardize, if I go by calculus, it will take forever. So standardization facilitates probabilistic, easy probabilistic computation. If I can do something in an easy way, why am I disturbing myself going the hard way? Okay, so I'm going to stop my share now. I'm going to go back to the material. Now you know, we've gotten that, right? How do I actually how do I do this one? Okay, I will check in the table for 2.38. I will check in the table for 1.05, then I will subtract them. Does that make sense? Okay, so here you're actually going to first check for this one in the table. Okay, and after checking for that in the table, you check for the other one in the table, then you subtract them. That's what you're going to do. Any question on that? How do I do the greater than one? I will check 1.75 from the table. Whatever I get, I subtract it from 1. Does that make sense? Now, is there any difference between this? Any difference? No, they're the same. Okay. And so all of that is super easy. Okay. Now, we're able to make use of the table because of the fact that we actually standardize. The essence of standardization is to facilitate easy probabilistic computation. Do I have question, whether in person or online? Is there any question, either in person or online? Okay, now I actually want to move to inverse normal. When do we use inverse normal? Okay, you know that for instance your z-score, you know that your z-score is actually x minus mean over standard deviation. Let me also tell you, what is the essence of z-score in statistics? The essence of using z-score, apart from facilitating easy probabilistic computation, the z-score enable us to compare the position of a data with uh with the rest of the observation. I want to compare the position of the data set, or probably with the average. For instance, your score. You have a score, and we want to look out about your score with the rest of your colleagues. Okay, then it means I'm actually going to I'm going to compare your score with the mean. Maybe you write an exam and somebody scored 90. What is your position in the class relative to others? I can make use of z-score. Okay, now when I compute z-score and it is 0, you know what I mean? S is your score, mu is the average score in class. Then it means your performance is equal to the average of the class. If the z-score is negative, then you are below the mean. It means your score is less than the average. If the z-score is positive, then you are above the mean. So for instance, if I have z equal to 2, that means you are 2 standard deviation above the mean. When z-score equal to 2 standard deviation. So z-score represents the number of standard deviation from the mean. I'm going to say that again. Z-score represent the number of standard deviation from the mean. If z-score equal to 0, then you equalize the mean. If z-score is negative, then you are below the mean. If z-score is positive, then you are to the right of the curve, you are above the mean. Does that make sense? Now, in the inverse normal distribution, if I know the z-score, can I have a way to compute my score? That is inverse. I know the z-score. I know the average, so which means this is what happened. Pay attention to what we want to do right now. Okay, so if z-score is actually x minus mu over standard deviation, then I don't know my S score. I know this z-score. I know the parameter. Then my S score is going to be z sigma plus the mean. If you solve that equation for S, okay? Now, how do we invert? How do we figure out this X? Is the priority on this page. And that's what we call inverse, okay? Now, we can see make use of the table to do that. Now, I need you to pay attention to how I'm going to do the example. Take a look at this. 1 second. I think that one is too sharp. I'm going to use this guy here. Okay, take a look at this guy. Okay, they've checked a table for you and you got a 0.0778. The question is, can we figure out what we check? What values of z-score that we check to be able to arrive at that? Okay, now the values of this score that we check, if I really want to know, like I said, I need to be able to fall first. That means I want to use this formula here to get my x. Okay, I want to do that to get my x. Now, you know what I'm going to do here? Oh my God. I'm going to go to the table, in the body of the table. I'm going to check for 0.0778. Then what was the corresponding z-score for that? You know, initially we normally check for z-score, but this time around, we're going to check from probability to be able to retrace the z-score. Okay, now I'm going to stop my share. I'm going to share. What was that? I think it was, let's go back. It was 0. Do you see that? It's 0.0778. It's 0.0778. Okay. is 0.0778. I'm going to share that now. It's 0.0. Now, take a look. I'll be searching here for 0.0778. Okay. Now, maybe it's going to be around here. Okay. It's 0.0778 is what I'm looking for. Okay, it's 0.0. Can you see this? Oh my God. Look at that. It's right here, right? If it is right here, what was the corresponding z-score? That is what we want to figure out. Then I'm going to say my z-score is negative 1.4 under 2 because the first column is 0, 1, 2. So my z-score now, so it means what I check that gave me that, okay, my x value now that I actually want to figure out is negative 1.42, okay, which means if I check for negative 1.42, it will give me this guy. It's like going backward. That is what we call the inverse. Does that make sense? Now I'm actually going to stop my share. I'm going to go back to the material. Okay. Now, that is what we mean by, the inverse normal. But let me tell you this. How do I do this? If I want to do this one, you can see they say Z, line between that and that. What I'm going to do, I'm going to first write the probability of Z, okay, less or equal to K, right? Minus the probability of Z, okay, less than negative 2.88, okay, and what is that? Or equal to 0.85, right? What am I going to do? I can easily check this one from table, right? If I check that guy from table, then I want to solve for this guy. When I solve this one from table, I'm going to add it to 0.85, right? Then I want to find this one. So it's going to resolve into the probability of a z less or equal to k. Okay. Now it's going to be equal to a value. Whatever you check from table for this, you add it to this because this is negative. Then what you're now going to do, you need to go to the table and do the inverse. Okay. Now, that is for that. You can go through all of that. And right here, okay, I'm expecting you here to four of us, like in this question now, where you have a greater than, to four of us do 1 minus P of Z, because the table does not have a greater than. The table have a less than, so I'm going to say less or equal to K, okay, equal, oh my God, equal 0.25, okay. Now you know what I'm going to do. I'm going to first subtract 1 from both sides, okay. If this guy should come here, I'm actually going to have, I think in the end, I'm going to have P of Z less or equal to K, okay, less or equal to K, equal 0.75, okay, right? Then you know what I'm going to do? I'm solving for K, then I will go to the table, okay? I'll check the body, inside the body, the probability side, the body is 0.75. I want to be able to identify the corresponding z-score. Does that make sense? With the table, you're actually going to be fine. It's going to be super easy making use of the table. Okay, now, let me tell you this. How am I going to tell the world that standardizing, okay, the shape doesn't change? If your data set follow normal distribution, if I standardize, the distribution will be normal. If your data set follow a different distribution, if you standardize, standardization does not change the shape of the distribution. Does that make sense? But the essence of the standardization is just for us to have an easy probabilistic computation. We actually want to avoid rigorous calculus. Now, take a look at this. If I have a data set, it followed normal distribution with a mean of 64.5 and the standard deviation of 2.5. This is going to be the curve. You know what this guy mean? This is what I derived the other time, that within one standard deviation is be 68%, within two is going to be 95, within three is going to be 99. After standardizing, okay, then I'm actually going to have mean to be 0, the standard deviation to be 1, but the shape still remain the same. Does that make sense? Standardizing the distribution of data set does not change the shape. If you have normal data set and you standardize it, it's going to remain normal. If your data set follow a different distribution that is skewed, after standardizing it, it's still going to be skewed. Does that make sense? Okay, now moving away from there. Now, okay, what is a real life example of on this? Why do I care about using normal distribution? Why do I care about standardizing? Take a look at this example. Okay, I told you the other time that you know um um real life data set normally follow normal distribution. Some real life phenomena follow normal distribution. Let's take a look at this example. The length of woman pregnancies from conception to birth varies, which means there's an uncertainty around the length of woman pregnancies. Okay, now according and varies according to a distribution that is approximately normal. Maybe we study the data set, we realize that 68 about 68% of the data set fall within one standard deviation, 95% fall within two standard deviation, and 99.75% fall within three standard deviation. Because of that, we conclude that the data set approximately follow normal distribution. When we're doing research, okay, before you can conduct any statistical inference on your data set, you need to get to know your data, like what distribution your data follow. Now, if your data set follow normal distribution and you want to compute probability, okay, you want to compute probability. If you follow normal distribution, then start celebrating, because to compute probability would be easy, because since it follows normal distribution, the idea of standardization can be used. Does that make sense? Now, but when they give you that it follows normal distribution, then you have to be given the mean and the variance, or the mean and the standard deviation. Right now, they said with the mean of 266 days. Now, that is just an average for the length of woman pregnancy. We have some that are more than 266, and we have some that are less. We live in a stochastic environment where there's variation, there's uncertainty around us. And they gave you the standard deviation of 15 days. That, okay, if I have the average of 266, if it is going to be more, it's not going to be more than 15 days. If it is going to be less, it's not going to be less than 15 days. Now, let's take a look at the question. What percent of pregnancy lasts less than 240 days? Look at that. When they say what percent of pregnancy lasts less than 240 days, okay, it is not 100% of pregnancy that will last less than that. So whenever they say what percent, then they want you to find probability. Don't be scared when you hear probability. Probability is talking about the frequency of occurrence. Now, right now, I need to interpret this guy. Please pay attention. I'm going to interpret this guy statistically, that what they are talking about, they want to find the probability of X. If I let X to represent the length of woman pregnancy, then it means they want you to calculate the probability of S less than 240. Does that make sense? They wanted to calculate the probability of S less than 240. But if I want to calculate the probability of S less than 240, if I should use a normal density, I'm going to run into rigorous calculus. But you know what I can do? I can standardize that. Instead of me to be looking for probability of S, I'm going to be looking for probability of Z. So I'm going to say to the world right now that using the formula for Z score, I'm gonna have the probability. Okay, I'm gonna have the probability of Z. Okay, less than, because they say less than. I'm gonna say less than. Okay, X minus mu over standard deviation. And of course, your mu is given to be 266 days. Your standard deviation is given to be 15. And your random variable S is 240. So you're actually going to do 240 minus 266. So it's going to be, so your Z is actually 240, okay, minus 266, okay, divided by 15. Okay, so if I use, I think I'm going to have using my calculator here. Okay, 240 minus 266 divided by 15. That will give me negative 1.73. Now, do you now know what I'm going to be looking for now? I want to find the probability of Z less than negative 1.73. So which means the probability of X less than 240 is the same as the probability of Z less than negative 1.73. Now, how can I interpret? Can somebody tell me? If you want to, if you do this in the hospital and the pregnant woman said, what are you talking about? What is the meaning of your Z? What does Z of negative 1.73 talk about in within the context of this study? If you want to tell everyone, yeah. You say what? Yeah, because it's not in the person that you try, but that pregnant woman is not in statistics. How can you interpret that negative 1.73? Okay, what is less than the average? Exact, which means, uh, we're talking about the length, the duration of the pregnancy from conception. So let's say you compute this for a particular woman. Maybe a particular woman deliver in less than 240 days. What you are trying to do, you are comparing that 240 with the average. Negative 1.73 means that woman fall in that category of, the number of standard deviation from the center is 1.73, like negative 1.73, which is below the average. Good job. That's a good one. Now, the same thing you're going to do when you get to the question B. Question B say between. You have two things to standardize. You standardize 240. You also standardize 270. So initially, this is going to read as the probability, okay, of X. Okay. 1 second. Just 1 second. Okay. Because I have camera I have a notification that somebody's at my door in my house, and my wife and children, they are inside sleeping. So, but it's mailman. Okay, so here I'm gonna have less than 240, right? And 270. Then I'm gonna standardize the two. When I standardize the two, then what I'm gonna have in the end is gonna be Z line between certain number, right? That's after standardization. Maybe you get A, I'm just assuming, and you get B. Okay, you're not gonna, here you're gonna, for the 270, the 270 is gonna be 270 minus 266 divided by 15, and that one. Then when you now have that, don't forget that you're gonna, when you go to table, you first check the upper bound, right? Then minus the lower bound. Does that make sense? And that is how you're actually gonna do that. Okay, and here, oh, because if you take a look at that very C, what are you gonna use? It say how long do the longest 50% of pregnancy last? You're actually going to use the idea of inverse normal there. Okay. Now let me move. Now the next I'm going to talk about before I go is at times we can use normal distribution to approximate binomial. Okay, for binomial we use it to model events with two possible outcomes. Situation when the sample size is large, we can use normal distribution to approximate binomial. But how are we going to take a look at this? Please pay attention. Okay, when S follow binomial, okay, we can actually, as n tends to infinity, as n become large, how large is it large? Then we have to do this. You have to see if n multiplied by p is greater than 5, or n multiplied by 1 minus p is greater than 5. If that happens, then you can standardize. But in the standardization, S minus mean is going to be the mean of binomial. The mean of binomial is NP. The variance of binomial is NP into 1 minus P. So here, we're actually, I think Jacob Bernoulli did this in 1733 when he was using normal to approximate binomial process, because when the sample size is large in binomial, it should be cumbersome to compute. And that's why we need normal approximation. But we got condition under which that is going to happen. Now, I need you to take a look at this example 6.5. Suppose that S is a binomial random variable with parameter n equal to 12 and p equal to 0.4. Find probability of S equal to 5 using binomial formula. Of course, you've done that. That will be easy. Okay. Now, let me tell you this. Please pay attention. Pay attention. With binomial formula, I can get this guy out. But if I want to use a normal approximation to binomial, binomial is discrete, right? And normal is what? Continuous. Then I have to convert discrete. You are given 5 here, right? If I want to use normal, I'm going to subtract 0.5, then I add 0.5. When I subtract 0.5, then 4.5 will be the lower bound, and 5.5 will be the upper bound. Then I can use the normal approximation. Now, if I want to use the normal approximation here, you know what I'm going to do? Okay, I want to find, please pay attention. I want to find this guy. I will standardize. What am I going to use to standardize? If I want to standardize this one, it's going to be 5.5 minus mean. What is the mean? For binomial NP, you're gonna multiply 0.4 by 12. Okay? Divided, what is standard deviation? Square root of NP 1 minus P. Of course, you know your N is 12, you know your P is 0.4. With that, you will have 5.5 standardized. You will also going to standardize 4.5. Then you use the normal principle that we always do, that we check from normal. But you know what they wanted to do in C? They wanted to compare your answer. Compare when we use binomial to when you use the normal approximation to binomial. Okay, in C. But let me tell you this. The one that will be correct? The one that will be perfectly right is the binomial. But the normal approximation will give an approximate answer. Does that make sense? Because there's always going to be an error that will come with approximation. Okay, so you can do the same here. So you can see when you want to find between 6 and 8, you subtract 0.5 from 6 and add 0.5 to 8. But let me tell you this. How do I know which one, how to add and how to subtract? This is the law. This is the rule. Please pay attention. This is very, very crucial. If you want to use a normal approximation to binomial, okay, normal approximation, because I need to convert from discrete to continuous. Discrete is binomial, continuous is normal. If I want to use the idea of normal for discrete, for binomial, I need to make a conversion. This is the continuity correction that we're doing. For instance, if they ask you, please pay attention to this. This is very crucial. If they ask you to find this, close at both ends, then to that value A, you subtract 0.5. To the value B, you add 0.5 before you actually standardize. That makes sense? If it is this, open at A, close at B, you add 0.5 to both. If it is close at A, open at B, subtract 0.5 from A and subtract 0.5 from B. If it is open at both ends, add 0.5 to A, the lower bound, and subtract 0.5. So we don't just subtract and add. We are guided. This is continuity correction, because if I want to approximate a process, approximating a process with something else will not give you exact answer. There's going to be an error. And we can minimize the error through this. This is a way of minimizing error that has to do with the approximation. That is why we call it continuity correction. That makes sense? Okay. Now, based on this principle, you know what to do here. Do you see that? What happened here? What happened to this one? Open at what? At both ends. Do you see? When it is open at both ends, what are you going to do? Okay. So you know what to do. Also, it's not. Oh, okay. So now this is the continuity correction. Now you can solve a problem. Lastly, my last 3 minutes, I'm going to talk about linear combination. If a random variable follow normal distribution, the linear combination also follow normal distribution. Take a look at this. If I have x1, x2 up to xn, they are independent, and x1 has a mean mu1, x2 has a mean mu2, xn has a mean mu_n. I want to talk about the linear combination. Okay, you've done that before. Okay, take a look at this. The linear combination is y. Can I find the mean of y? Can I find the variance of y? Of course, the mean of y is going to be this. Don't forget, each of x1 has the mean, mu1, s2 has that. What will be the variance? Then the variance of x1 is sigma 1 squared. Don't forget, the constant is also going to be squared. We've done this before. Now, if I now ask you, what is the distribution of y? Then you're going to tell me y follow normal distribution with the mean of this, because this guy, the formula is that. Can you see that? And this is for the variance. If I put a square root on that here, I'm trying to say the standard deviation. Now, this guy is the same thing as this. Writing this guy in short form, which is the same thing as y. Can you see that? Which is this, give me 1 second, which is the same thing as y. Can you see that? So if x1, x2 up to sn follow normal distribution, the linear combination of that also follow normal distribution. Okay. Lastly, I think we should be on the last page now. Okay. This is what we're going to do next. We've done under the probability distribution for continuous random variable. We've done continuous uniform. We've done normal distribution. And The next this set of distribution we're going to do in the continuous family is exponential, gamma, and chi-square distributions. Okay, I've already uploaded the material for them. Okay, so make sure you all stay safe and have a lovely day. Bye for now, everyone.